is f of Tn yn plus f of Tn plus 1 yn plus 1 all over 2. So we're going to average those left and right bounds. Okay? That's the basic idea. But what is there anything we don't like about this? Yes, there's a yn plus 1 on both sides. So we could still go through with this and just substitute yn plus 1 into our formula. But depending on how difficult that f function is to solve, it might be really difficult to solve for this yn plus 1, right? That's why we don't like things that are implicitly defined, where what we're looking for is on both sides of the equation. That could be really challenging to solve. So what I want to do is I want to find something different I can put here for yn plus 1. The Tn plus 1 is not an issue, right? Because we just get that by adding h. So that's not a problem. It's this yn plus 1 that's causing a lot of problems. So we are going to kind of iterate and look back at Euler's formula. So remember, from the original Euler's, we have that yn equal, or yn plus 1 equals yn plus h f Tn yn. Okay. So what we can say is we're going to use this for our yn plus 1 on the right. So yn plus 1 is going to equal yn plus h times f of Tn, yn plus f of Tn plus 1 yn plus h f Tn yn. So we are using Euler's inside this improved Euler's. This is definitely a little notational heavy. So what you'll often see is, to make it just look a little bit nicer, people will let Fn equal f of Tn yn, because that term comes up a lot in this equation. So just like cut down on the notation, they're just like, let's call Fn f of Tn yn, and then you can rewrite this as yn plus 1 equals yn plus h times Fn plus f of Tn plus 1 yn plus h Fn all over 2. And what this also allows you to think about is kind of breaking down the steps a little bit more. You know you were going to need this f of Tn yn quantity 2 times, so go ahead and calculate it, and then you can just substitute it into this formula and make your life just a little bit easier. So the error bound for our improved Euler, our local error bound, I should say, is En plus 1 equals 1, 6, B triple prime of, I'm going to go 1/6 or m over 6 h cubed, where m, again, is that max, but this time it's going to be the max of b triple prime on our interval a to b. Is this error better than Euler's? Original Euler's? Should be. Why? Because it's improved. The name says it all. Yes, that is true. Any ideas why, though? When we talk about h, is it normally a number less than 1 or a number bigger than 1? Less than 1, right? H cubed then is going to be less than h squared, right? So you're bringing that error down. I mean, we still have this m, but maybe for whatever reason the triple prime is larger, but overall, because we have this h cubed, it's going to shrink that error versus the h squared. All right, questions about that? So calculating improved Euler's is really just a pain. I'm not going to lie. It's not fun to do by hand. But on your assignment, I do want you to go through one iteration by hand just so you can work with it. So on C, I'm asking you to do one iteration of the improved Euler's. And then D, give me what step size we would need to bound the local error by 0.0025. Okay? Perfect. Thanks.